All right, so this is our first presentation on Chapter 16 on thermodynamics, entropy, free energy, and equilibrium. So key points for Chapter 16 for Test 4, spontaneous processes, free energy and spontaneity of chemical reactions, free energy changes of reactions, free energy and chemical equilibrium, entropy, going into various concepts of entropy and probability, entropy and temperature, molar entropy, entropy in the second law of thermodynamics, and we'll talk a little bit more about what entropy is and how we can define it and how we can best think about it too in this section. Again, like previous sections, we're not going to be focusing on counting little balls or reading charts and diagrams and such on the exam. We'll take a look at them, we'll understand them in the material as we review, but we won't be focusing on that on any test or exam questions. So let's take a look quick at some key terms. So thermodynamics, this is the area of science that deals with the interconversion of heat and other forms of energy. A spontaneous process. So we'll delve into this in a little more detail as we move ahead, but a spontaneous process is one that proceeds on its own without external influence. Now this is a term of art and it means something very specific. So we'll delve a little bit more into parsing out exactly what these words mean and how exactly that refers to things, right? The word spontaneous can be a little vague, but we'll delve into it in more detail. Similarly, entropy, right? It's got kind of a complex concept, right? So it's a thermodynamic state function, which we'll talk about in a little bit, measuring the dispersal of energy per unit temperature for a specific configuration of a system or microstate. A lot of books, and even this one, will talk about this as like a kind of randomness. It's probably better to think about it like a dispersal of energy, like a spreading out of things in different modes that particles can enter into, and how likely the state is that something currently is in. More likely states have higher entropy than less likely states. We'll see how that works in a little bit as we delve in further. So free energy. Free energy is another state function, another thermodynamic state function, representing the maximum amount of thermodynamic work theoretically obtainable from a system at constant pressure and temperature. Now, if you're not familiar with the idea of work, this really goes back to like Chem 151 and concepts that were presented there. There'll be some material available earlier in the course with review, where we can look up a little more about that if this is something that you don't quite remember. But we will be building on concepts from 151 here, and assuming that you understand like about heat and work, the basic ideas of that. When a change in free energy is negative, a process is spontaneous. So that's another way to think about what a spontaneous process is, as an available free energy in the system is used up. When a change in free energy is positive, a process is non-spontaneous, as free energy has to be put into the system externally to power it. And finally, when the change in free energy is zero, the process described results in no change from thermodynamic equilibrium. So a process's equilibrium has no free energy change when that process occurs, because there's not really a process, it's just a system in equilibrium. So let's talk a little bit more about state versus path functions. So a state function is a process or some kind of function that we could describe with a simple final minus initial mathematical formulation, usually designated with a capital letter and a capital delta sign, the little triangle. An example of this is the absolute and shortest, like as a crow flies, distance between 2 points. So like if we were going to go on a trip, the actual distance you drove is the path function, but the physical distance between the 2 points, the absolute distance between the 2 points, is a state function. So a state function describes something that doesn't change with how something is carried out, right? Thermodynamics generally covers state functions and is pertaining to state functions. It doesn't change in how you do it, just that it happens is all that's important. Whereas with path functions, it matters how something is done, right? These are functions that can't be represented with a simple final minus initial. They usually have a lowercase letter and a lowercase delta sign. These functions incorporate how a process is actually carried out, like I said, like the real distance you might drive between 2 points. Or from a chemical standpoint, the kinetics, like how a reaction actually occurs, how fast it occurs, etc. These are all path functions, right? Because if you have a catalyst or something present, like the reaction might go faster. But the actual position of equilibrium, that's a thermodynamic point. We'll again talk a little more about this in detail, but I wanted to give you some sense of sort of where these terms are as we use them. Finally, I've got a discussion of the laws of thermodynamics. We'll talk about the first, second, and third through the context of this chapter, but I've also got the 0th law here, which really has to do with the idea that all heat is the same. So two systems in thermal equilibrium are in equilibrium with another system if they're each in equilibrium with that one, right? So we can define all heat as being the same. It doesn't really matter where it comes from. First law of thermodynamics, any process, as a result of any process, the total energy of the system and its surroundings or the universe is constant. Whenever they say like system and surroundings, they're really referring to like everything, total energy in everything. The second law of thermodynamics says that any spontaneous process must increase the entropy of the system and its surroundings. So together, like one of them could go down and the other one go up, but overall there has to be an increase in entropy as a result of a spontaneous process. So that's where this idea that the entropy of the universe increases with spontaneous processes comes into play. And finally, the third law, that the entropy of a perfectly ordered crystalline substance is zero at 0 Kelvin is 0. So it's got to be perfectly ordered. Not all substances can reach this configuration, and it's also got to be at 0 Kelvin in order to be 0. Now, there's no way to actually reach 0 Kelvin. It's kind of like a theoretical point, but this allows us to define a 0 point for entropy. And I'll kind of move a little out of the way to make sure you can see that a little more clearly there as I've moved while talking. So let's talk a little more about a spontaneous process, right? So we said a spontaneous process is one that proceeds on its own without any external influence, right? The reverse of such a spontaneous process is always non-spontaneous and needs some kind of external influence. So what do we mean by an external influence, right? We can think about that as like energy being water freezes spontaneously. So I take the cup and I put it in the freezer and I close the door. Inside that freezer system, water freezes spontaneously. But we know that the freezer would not be cold inside unless it was powered, because it's got some kind of temperature gradient with the surroundings that's being generated by energy that we're putting into the freezer, right? So we have to define where exactly the system is, right? So with regard to the system, water freezes spontaneously. But with regard to everything else, there's power to keep the freezer where it is and all of that, but we're not really concerned with that when we talk about like the water cup system, right? So that's where this spontaneous idea comes from. I'm not having to do any kind of influence as not looking at the whole freezer system, right? The freezer getting cold is not spontaneous. That has to be powered externally. But anything that goes on inside the freezer relative to the things in the freezer, those freezing processes are spontaneous. That makes sense to kind of help explain the distinction between spontaneous and non-spontaneous and systems and surroundings. Again, this is a more technical term that was discussed more in 151 in the concept of like work and heat. But we're going to assume we have a good understanding of it here. But I just wanted to give you a little review in case you never quite saw like what this means. To say something spontaneous specifically means in this context, right? Specifically means under some certain temperature, pressure, setup conditions, this process occurs without the need for some kind of external energy being put in, whether that's from something being wound or something being charged electrically or something else driving it. It simply occurs. And when they say that, they don't mean like the heat at that temperature is excluded. So endothermic processes or something like that might need to absorb heat from the surroundings can be spontaneous as long as at that temperature they have that energy available. And we'll see the connection between spontaneity and temperature and such like that as we go along as well. So, for example, it is spontaneous for an ideal gas contained in this example A here to spread into the B container, but it's non-spontaneous for this to happen in reverse. And again, this is because as the system spreads out, as we spread out energy, we spread out the particles so that they're in a more likely configuration. It's more likely for these to be spread out than to all be concentrated once this stopcock is open, right? Once it has the possibility of achieving that state. Again, we'll talk more about that as we move through different parts of the material. So we talk here about a reaction, right, where hydrogen and oxygen combine to make water. This forward reaction is spontaneous, but the reverse reaction does not occur no matter how long we wait. This reaction essentially goes to completion if we think about it in terms of equilibrium. The equilibrium is so far in the product's direction that there's essentially no reversal. We don't see anything like that significantly going on. We could force it to happen, but we'd have to apply some kind of electrical energy. So that helps to distinguish a spontaneous from a non-spontaneous process. Some reactions have an equilibrium where the amount of products and reactants are much closer together, but still, in order to move something away from equilibrium, I'm going to have to apply some kind of energy in order to perform that shift. Otherwise, the system will move toward wherever that equilibrium value is set to. Now, depending on where my conditions start, right, then the forward or the reverse reaction could be spontaneous in order to establish the equilibrium that's necessary. So a movement toward equilibrium is always spontaneous. Keep that point in mind as well. A spontaneous reaction always moves the mixture toward equilibrium. Now remember that spontaneous doesn't mean fast. Spontaneous just means that's the direction that the system tends to move in given the certain set of conditions, right? Because the position of equilibrium changes with temperature, like we've already seen. So we can see that at different temperatures, it might be that one direction or the other might be spontaneous, and that's okay. Thermodynamics tells us where the reaction is headed. It does not say anything about how long it takes to get there. Keep in mind that distinction. That it may be a very slow process and still spontaneous based on whatever the kinetics are for that process. It depends on the activation barrier. Again, this is all information from previous chapters. We're just integrating here and reviewing to make sure that we understand why a spontaneous process might still be slow. So initially, I mean, there was a thought with the 19th century chemists here that are discussed that a system that's exothermic, right, that exothermicity has something to do with spontaneity, right? Most systems that are exothermic are also spontaneous, but not always. And it also turns out that some processes that are endothermic are also spontaneous, right? Obviously, right? So like ice, for example, spontaneously absorbs heat from the surroundings and melts above 0 degrees Celsius. That melting process absorbs heat from the surroundings and it is spontaneous. It obtains its energy only from the ambient temperature that's available. It doesn't get it from any other kind of external source, so it's defined as spontaneous, right? So not all, like exothermic processes sometimes are spontaneous, but that's not the only parameter that must be defining things, right? Liquid absorbs heat and spontaneously boils at a temperature above 100, right? Depending on where we define the system. If I define the system as the liquid that's inside the pan when I boil it, then the pan is above the boiling point, so the water boils. You know, I would, depending on how exactly I delineate my system, I can say that the water will spontaneously boil. If it was on the surface of the planet that was just at that temperature, then water would spontaneously boil, right? Further example, they talk about gaseous N2O4 that absorbs heat and decomposes, and table salt absorbs heat when it dissolves in water as well. So some processes that are endothermic definitely are still spontaneous, at least at a given temperature, right? At whatever the temperature is set to. So this is where the other parameter of thermodynamics comes in. We know that the first parameter is heat, and heat at a constant pressure is our enthalpy, is the delta H that we'll see through this chapter, right? But we've also got this idea of this delta S. This delta S is the entropy, right? And the text will call this some kind of randomness, but instead we could probably think about it as like a spread out of energy. Because it's not random. The tendency is not random. It's not like it just picks something, some outcome at random. It always moves toward a likely state of energy dispersal. And a way to think about it is like, if I flip a coin enough times, I'll get about 50-50 heads and tails, and that'd be the most likely outcome. That's kind of similar for entropy. Entropy is that tendency to likely outcomes, a way of dispersing, because it's very unlikely I would just get all heads unless something is rigged, right? Sometimes there's something that's rigged or something is prevented from happening. Two things are prevented from mixing together because of something. So that can affect like why I might see something the way that it is, right? Entropy defines that given nothing else, energy is going to disperse. Things are going to want to be a gas. It's going to want to get more spread out with space. Work is going to become harder to collect and use to perform processes with. We'll talk all about that. But entropy incorporates all of these ideas. Yeah, that's why I say, like, I think randomness can be sometimes a bit misleading as a term. But much like other thermodynamics functions, it's a state function. So the final minus initial can describe any entropy change in a process as well. So if we move particles around more, like if particles move around more, or if they're in a state, in a phase that's more fluid, then they have more entropy. So we can look at a particular state of the system, like the molecules in a liquid state versus being in a solid state, and say that the liquid state has more entropy just inherently because there's more ways the particles can be configured. They can store more energy. They can be at a higher temperature. They can float all around. They can bounce into each other and everything like that. And that inherently has more entropy than the particles being stuck in a more rigid location. So we can make these kinds of statements and compare phases in different configurations of the system with each other in terms of changes of entropy. And we'll get into that in a little more detail too. Typically, being a gas has more entropy than being a liquid than being a solid. That's the general tendency of these systems, because that increases the different configurations that the particles can be in, and they're freer and they're able to achieve more modalities. So they can put energy in more different forms, as a way of thinking about it. Like a water molecule can spin more or move more or be in different positions. Energy is dispersed out through the system better when it's a liquid than when it's a solid, where all the energy might have to just be little vibrations. If all energy is kind of in the same form, that's less entropy than if it's spread out in more different ways. Keep all of this in mind. So they give us a little example here where they say that the solid here has less entropy than the liquid has less entropy than the gas. And that these processes, melting increases our entropy, and then freezing decreases entropy. So entropy becomes negative, the change is negative when we go down this scale, and it's positive when we go up this scale. Also, the decomposition of some kind of molecule into more particles also increases entropy. So if a reaction increases, often particularly the number of moles of gas, then that increases entropy as well. Getting more particles is good entropy. It scatters out energy into more various ways. So it also increases entropy. Dissolving increases entropy. So when something gets dissolved into something else, it gets spread out through that thing, and that increases entropy as well. So they say to predict the sign of entropy for these processes, right? So when dry ice sublimes, when it goes from a solid to a gas, that's positive entropy. When a solid decomposes into a solid and a gas, because of the addition of a gas, that increases entropy. When 4 moles of gas become 2 moles of gas, as in C, that's negative entropy. That's bad. Generally, we want more moles of gas. We want to spread things out into more states. And when something dissolves, like iodine dissolves into water, then entropy is positive, because that's a dissolving process. These are sort of easy questions that you might see in the homeworks or in other examples, just to test, do you understand the basic principles of entropy and judging the difference in entropy between different states, in kind of a broad way. Like I say, now the text kind of goes more into this entropy as a probability thing, which again I think is probably the best way of thinking about it. They say I've got a box full of identical coins, and if I shake the box, it's unlikely that all the coins will come up heads, or all the coins will come up tails. If that happened, you might think there was something wrong, like some kind of shenanigans or something going on. The likely states are the ones that we expect, which are all the different ways that the particles could be configured in such a way that there's about half heads and half tails, approximately. That's what we would assume, and that's because there are a lot of different ways to get that state. There's a lot of different ways to get a bad hand, but in that sense, only a few ways to get a royal flush. So it's just simply a matter of probability, and that's typically how we think about this. We have lots and lots of particles in thermodynamics, moles and moles of particles. So the odds that all the particles will be aligned all in one direction and move all together in one direction is just extremely unlikely. So those states, we just don't observe them. We observe the states that are most likely, and that makes sort of reasonable sense. Like the things we observe are those things that are likely to observe. So they talk about all the different ways that you could get, there's only 2 ways that you could get all heads or all tails, but 2 to the 20 different ways you could get all different other configurations. So this includes all possible arrangements. They said no, a state with a random arrangement of coins includes all arrangements. So the odds of not getting these are just extremely high. Another analogous example, they have this CO molecule where they can be locked in different configurations as well. And they talk a little bit about this in some detail to see if maybe this could be a perfectly ordered crystal. It turns out that this one doesn't form a perfectly ordered crystal, but we'll see they'll pack only in one way that they could align themselves in that configuration. But the less ordered states are just vastly more likely. that show a perfectly ordered heads-up structure versus one where they're not. And this is most likely right about 10 heads and 10 tails is likely, so 11 heads and 9 heads and 11 tails is pretty likely too. You expect that there'd be approximately equal heads and tails, and that would be a likely state, whereas other states are much less likely. So here they talk about the Boltzmann equation, right? So what's interesting about Boltzmann is that he's interested in connections between things like temperature and different states, and in this case here, entropy and different states, right? This idea is that entropy is related to the number of states that this particle could enter into. That's what's related to this W, the number of ways the state can be achieved, right? The entropy of a state is equal to some constant times the natural log of the number of ways that state could be entered into. So if there's only one, then we'll see what ends up happening to that. But the more different ways that can happen, the bigger this number gets, and so the more entropy this state has. So they say here that if there's only one possible state, that the way we could get to this, then the entropy would be 0. So that's interesting. More probable states would have other values of entropy. So that's also important to think about. According to Boltzmann's equation, the entropy of a state with a random arrangement of CO molecules is this value. And based on experimental measurements, that's what we see. So it seems like at about 0, the CO molecules adopt a nearly random arrangement. So they don't adopt a perfectly crystalline arrangement as we get lower down. They have a finite entropy value. So we could get an idea of how much, if we could measure the entropy of a state, we could also figure out how likely that state is and vice versa. They talk here about having intermolecular dipole forces, and that would also help bring things into a more ordered crystalline solid so that maybe we could get closer to 0. They say HCl with a large dipole moment forms an ordered crystal solid, so the entropy of 1 mole of solid HCl at 0 Kelvin is actually 0. They also talk here about the expansion of an ideal gas, and they go into why the expansion of an ideal gas has favorable entropy. And they give us this example with breaking up a space into boxes and other sorts of things. And also just keep in mind that we intuitively know that expansion of a gas spreads things out more over more space, so we would expect it to increase entropy. But what we're looking at here is how we could also mathematically see that with the Boltzmann equation, right? So they're able to calculate this and higher the state, gas expands spontaneously because the state of greater volume is more probable. And they think about a general equation for this, breaking this up into boxes and then applying a final minus initial state in order to calculate the different ways that the molecules could be distributed over a box. Again, I'm not going to worry too much about this derivation process here. You review it for your edification, but ultimately what's most important is this final equation here, which talks about the change in entropy for some moles of gas times R times the change in volume of this gas. And you could also write this in terms of a pressure change as well. So it's interesting. You know, we can see that, of course, the relationship here is that we'll see an increase if the final volume gets bigger. The bigger the expansion, the more this increase in entropy for some given number of moles of some compound. So let's talk a little bit more about entropy and temperature here. So entropy is associated with motion, but not just like a motion moving, but also rotation within the molecule. More complex molecules can bend and twist and rotate on top of themselves, and that's a way that they can increase their entropy as well. Individual molecules have different speeds, and their speeds are associated with, you know, the overall average temperature. So you would imagine that if you increase the temperature of something, you'll have more states be accessible, right? So if you imagine that, like, if you have some particles, right, there's different bending and twisting and spread out distribution of speeds and all different things. So if you have more energy, you should be able to disperse it in more ways because more modes will be accessible. Like each mode has some certain energy associated with it, and more modes are accessible if you're at a higher temperature. So generally speaking, the entropy of a substance increases with increasing temperature as well. So generally at higher temperatures we see higher molecular speeds, broader distributions of kinetic energy, and more internal modalities and other things like that as we increase in temperature. And they mention here the third law of thermodynamics, that the entropy of a substance that's perfectly crystalline at 0 Kelvin will be 0 in order to define a 0 point for entropy. And we see that when melting happens, we have this discontinuity where we dramatically increase in entropy. We got a little statement here of the third law. Again, I also have that at the beginning as part of a review. And then they talk here more about the vibrational and translational and rotational modes that I've been talking about. This allows for a lot of the increase of entropy when you change phases, because more of these modes become available. Not just their ability to move back and forth over more distance, but also more rotational modes. It's also true that when you have different phases, like if you have multiple solid phases or multiple liquid phases for a substance, some phases will have more entropy than others based on how free the particles are to move within the structure of whatever this thing is. For example, like an amorphous or a metallic version of some element, right? The amorphous one will have more flexibility than a metallic one that's held with a metallic lattice. All right, so this is the end of this presentation. I hope I'll see you all in the next one, and I hope you found this very edifying. Thank you very much for joining me in this, and I will see you in the next one. Bye.